In addition to many of the monoatomic ions that we've worked with on the periodic table, another big class of ions that we're going to come across repeatedly over and over and over again are the polyatomic ions. So polyatomic ions are kind of an interesting class of things that have both ionic and covalent interactions happening at the same time. As their name implies, if we break that down, poly means many, atomic, atoms. So a polyatomic ion is a grouping of multiple atoms that have a charge. The majority of polyatomic ions are anions, or negatively charged, but we'll run across a couple of positively charged ones as well. One of the advantages of polyatomic ions is if you recognize a polyatomic ion in a chemical formula, you know that it has to be an ionic compound. It has to be an ionic formula because a polyatomic ion is always an ion. So that's one place where they can be really helpful. And just a personal note here, I try not to ask students to just memorize a lot of things. Lots of us have a limited quantity of storage space for memorized individual things. Polyatomic ions are something that it really is worth your time and your effort to just sit down and do your best to memorize a whole bunch of them, because if you always have to stop in a problem and go look up a polyatomic ion, it really impacts your ability to approach a lot of the other parts of the problem. So sit down and memorize them. It's like a vocabulary. It's like an alphabet for what we do. So put some effort into that. Let's take a look at some specific polyatomic ions. Your book includes this really nice graphic from Compound Interest. If you haven't looked at Compound Interest or compoundchem.com, they've got a lot of really good infographics that are presented in a really nice way. This particular one is polyatomic ions, named, formula, and charges. So here is not an exhaustive list, but here are a bunch of the polyatomic ions that it's worth your time to figure out a little bit about them. Some of the ones I'll pick out specifically here to look at are things like acetate. Acetate is a polyatomic ion that's 2 carbons, 3 hydrogens, and 2 oxygens. It has a -1 charge. That formula is written a couple different ways depending on where you see it, but that's acetate. Another one that you probably have heard of is cyanide, Cn-. So that's a polyatomic ion, carbon and nitrogen. Ammonium is one of the fun ones because ammonium is just about the only positively charged polyatomic ion we're going to work with, so NH4 plus 1. When we get to the oxygen family of things, hydroxide is a very common polyatomic ion that we're going to use in a bunch of different contexts. It's OH -1 charge. Another one that comes up every once in a while is peroxide. Peroxide is O2 with a -2 charge. Excuse me. Make sure you distinguish that from an oxygen molecule. That's an O2 that's neutral. This is peroxide, ends in IDE, so it's probably an anion, and indeed O2 -2. We've got some sulfur-containing ones that we'll get to in a bit. We've got phosphate, the chlorate family, and then a couple of down here. We notice that with all of them up here, these are all non-metals. So carbon, nitrogen, sulfur, chlorine, all non-metals. There are a few polyatomic ions that have transition metals in them. So chromate and dichromate. So chromate, chromium is a transition metal. CrO4 -2 is that polyatomic ion. Dichromate is Cr2O7, again -2. So structurally, that's what that one looks like. And permanganate is a very common polyatomic ion that we use in a number of reaction situations. So permanganate is MnO4 minus 1. Now I kind of skipped over a bunch of these because if you look at things like carbonate or nitrate or sulfate or chlorate, you see that there's some non-oxygen, non-metal element surrounded by some number of oxygens. So these, as sort of a broader class, are what's known as oxoanions. And fortunately for us, oxoanions have a systematic nomenclature. So we don't necessarily have to memorize all these individual oxoanions. What we really need to do is figure out one of them in each class and then use the nomenclature to help us name the rest of them. So if we're looking at oxoanion nomenclature, so anions, negatively charged species, which contain oxygen and some other element in the center, nomenclature, let's take a look at bromate, the bromine family of these, for example. So bromate, BrO3 minus 1. Well, there's another polyatomic ion called perbromate, which is BrO4 minus 1. So per8 is one more oxygen, but the same charge as 8. Bromate, perbromate. If we're at bromate and we go down one oxygen, so now BrO3 minus 1 to BrO2 minus 1, we've got bromite. So one less oxygen, but the same charge, goes from 8 to 8. And if we go one more oxygen down, BrO minus 1, we get hypobromite. And that is a systematic nomenclature system. So really, in this case, we only need to know one of these in order to actually know the name of 4 different polyatomic ions. Another thing about oxoanions is that they can be protonated. They can have H plus added to them, hydrogen. So if we've got a oxoanion that has a charge greater than -1, or I guess less than -1, more negative than -1, we can add H plus. We can hydrogenate those. We can add hydrogen. So if we start with, for example, phosphate, PO4 minus 3, we can add H plus to that to get to hydrogen phosphate, HPO4 minus 2. We can add another hydrogen to that, another H plus to that to get to dihydrogen phosphate, H2PO4 minus 1. So we're adding H plus, which means that that total charge on our oxoanion assembly keeps getting less negative because we're adding positive charge to it. Now, I mentioned that it has to be an oxoanion with a charge of at least -2 because once we add H plus, we still want it to be an ion. If we added, in this case, if we added another H plus to this, we would cancel out all that charge and we would no longer have an oxoanion. In fact, we would have, in that case, an oxoacid. That would be phosphoric acid. So some of them can be protonated. Carbonate, sulfate can be partially protonated. What about memorizing? Now, I said this is about one of the few things that I actually encourage you to just memorize. And this is a perfect application of flashcards. So whether you've got just a little pack of index cards that you can make your own flashcards, I encourage that, by the way, because writing all these out actually helps you memorize them. Or if you prefer to do it online, you can use some flashcards to help you out. If you search for polyatomic ion flashcards, you'll find a dozen different websites and examples that you can use. There are also a couple mnemonics. One that seems to come up a lot fairly recently is a mnemonic to help you remember what all of the ATE, the 8 oxoanions, are. Because remember, if you know what one of them is. If you know the ATE version, well, then you know the per 8 version, you know the ite version, you know the hypoite version. So, little mnemonic here. Nick the camel ate a clam for supper in Phoenix. How does this mnemonic work? Let's go through all of the capitalized ones here. If we look at Nick, the word Nick has 3 consonants, N-C-K, and 1 vowel. Well, nitrogen, capital N, nitrogen, has 3 oxygens, 3 consonants, and 1 vowel. Charge is -1. NO3 -1 is nitrate. Work through the rest of them. Camel, 1, 2, 3 consonants and 2 vowels. So carbonate has 3 oxygens and a charge of -2. Clam, 3 consonants, 1 vowel. Chlorate has a charge, or it has 3 oxygens and a charge of -1. Supper, 4 consonants, 2 vowels. Sulfate, 4 oxygens, -2 charge. And finally, phosphate, Phoenix, 4 consonants, 3 vowels, 4 oxygens, -3 charge. Once we know that 8 version, again, we can use that systematic nomenclature to figure out what the ite version is, the hypoite, the per 8, and help ourselves out there. So one of the big things with polyatomic ions, as with all ions, as with all ionic compounds, is we need to practice. We need to look at a lot of these. So find opportunities to practice wherever you can. Again, as I mentioned previously, one place that's actually really good for finding a bunch of these things just out and about wherever you might be are in food labels. So if you look at the ingredients in a food label, oftentimes you'll find some polyatomic ions. You'll find nitrates and phosphates and sulfates throughout there. So look at your food labels, and if you see something that looks like an ionic compound, try to write out the formula for that ionic compound just as some practice. See you next time.